Giglio Power Infrastructure Engineering, Advancing Power Infrastructure. In this video, I discussed the load transfer between 4 Trefoil cables to 2 smaller Trefoil cables based on my 2022 IEEE paper, Dynamic Thermal Model for different sized Trefoil power cables with various loads in non-forced ventilated tunnels. Out of the 6 Trefoil cables, there are 2 pairs of the cable type as highlighted here and rated for 230 kilovolts. Also inside the tunnel, there is a pair of cables of the type highlighted here and rated for 35 kilovolts. This algorithm directly computes full load ampacity, including transient ampacity, for any practical time duration, and it was first presented in my 2022 IEEE Early Access paper, of which this video and example is based on. The conductor temperature transients are dominated by the heat transfer dynamics of the tunnel wall and soil layers. Therefore, all the heat generated in the cables are transferred out of the cables via radiative and convective heat transfer. In this load transfer example, transient ampacity is computed for all cables for a 40-year cable operation. Therefore, all heat transferred out of the cable are partially stored into the tunnel wall and soil layers and partially transferred out of the soil layers into the ambient. The transient ampacity results for the 3 cable types are shown on the bottom right. This algorithm directly computes load transfer ampacity, and it was presented in my 2022 IEEE Early Access paper. In this example, load is transferred from the medium-sized and large-sized power cables to the smaller cables by reducing the full load transient ampacity by a fixed amount, in this case 40% for the medium-sized cable and 60% for the large-sized power cable. The load transfer ampacity values for the smaller cables are computed by fixing its conductor temperature at the temperature limit and using the resulting conductor heat rate to compute the current and finally obtain the load transfer ampacity values when the calculations converge. COMSOL Multiphysics FEM simulations were completed to validate the circuit model and verify the load transfer ampacity values for the smaller cables, which is showed a 63% increase in ampacity for the smaller cables. However, FEM time-dependent simulations showed that the maximum conductor temperature at 40 years reached 92.6 degrees Celsius, which is 3.71% above the temperature limit 90 degrees Celsius, which is not a problem since the industry allows a derating factor between 0.95 and 1 to reduce the computed ampacity. In this example, the ambient temperature is 20 degrees Celsius and the maximum conductor temperature rise is 70 degrees Celsius. Therefore, the minimum conductor temperature rise is 66.5 degrees Celsius and is used together with the maximum conductor temperature rise computed in FEM to compute the derating factor of 0.957, which is in the acceptable range for the derating factor. I applied the derating factor of about 0.957 to the full load transient ampacity at 40 years to the smaller cables computed with the dynamic thermal circuit modeled in MATLAB and applied this reduced current in a COMSOL Multiphysics FEM time-dependent simulation, which shows that the maximum conductor temperature reached about 87.9 degrees Celsius, which is below the temperature limit and within acceptable tolerances. Consider the complexity and challenges of modeling this nonlinear thermal system of a tunnel buried in soil and containing 6 Trefoil power cables of different sizes and carrying different loads, and being able to accurately and precisely compute the load transfer ampacity using a dynamic thermal circuit model developed completely in MATLAB using the IEEE standards and industry-leading texts such as Fundamentals of Heat and Mass Transfer by Ampacity and Fundamentals of Fluid Dynamics by Munson. To be able to accurately compute ampacity within acceptable tolerances, the engineer must be well-rounded in multiphysics, especially in electromagnetics and heat transfer, and must be knowledgeable and experienced using the standards, codes, and manufacturer data sheets, in addition to being proficient with setting up and running FEM and CFD simulations. I choose to use COMSOL Multiphysics because of its user-friendly interface and workflow, which allows to easily set up multiphysics models. In particular, for power cables, they do have application and libraries for power cables as shown here. That is all. Contact Giglio Power Infrastructure Engineering, Advancing Power Infrastructure, if you would like fully detailed multi-physics modeling and solutions for your projects.